Okay, so today we're going to look at the problem where the definite integral goes from 1 to 2 and is of dx over the square root of x times the square root of 4 minus x. The first thing we want to realize is that these are x bounds. The second thing is that when I look at this, I see that square root of x in the denominator, which usually lends me to the substitution where u equals the square root of x and du equals 1 over 2 square roots of x dx. And I do that substitution because now the dx over the square root of x is going to come from my du function. So I'll get the definite integral problem. Instead of the dx over the square root of x, I'll have 2 du, and then in the denominator I'm going to have the square root of 4 minus u squared as I solve that substitution for x. I also need to change my bounds back, and when I do that, I plug 1 in for the square root of x, which is still 1, and I plug 2 into x for the square root of x, which is the square root of 2. And this integral starts to look a little bit more like a inverse sine function. The deal is that I have got to take that 4 there, and I need that to be a 1. So the first thing I do is I'm going to divide everything in the denominator by that 4, which is technically under the square root sign. So to balance this out, I'm going to need to multiply the top by 1/2. Again, that's because the 4 is technically under the square root sign. What that's going to give me now is that I'm going to have the definite integral as of du over the square root of 1 minus u squared over 4. And don't forget about my bounds here. My bounds are still going to be u bounds, and they're going to go from 1 to the square root of 2. Now this becomes a double substitution problem because in order to integrate this, I need to make this double substitution where w, in this case, is equal to u over 2. And that way when I do dw, I'm going to get dw as 1/2 du. So going back and creating some simple substitutions here, what I'm going to get is a definite integral, and in the top, instead of du, I'm going to plug in 2dw over the square root of 1 minus w squared. And that's the benefit of making the substitution that we did. And I also need to now create and change my bounds into w bounds, and I do that simply by plugging those values into u for the substitution I made, which is going to make the lower bound 1/2 and the upper bound the square root of 2 over 2. Integrating this is going to be pretty straightforward. Don't forget I have that constant of a 2, and then I'm going to have my inverse sine of w, and I'm going to evaluate that inverse sine of w for when w goes from 1/2 to the square root of 2 over 2. The expectation is that you can do this kind of stuff by hand and without a calculator. So let's just finish walking right through this. Our fundamental theorem of calculus says that in order to evaluate this, we're going to do top minus bottom basically. And so we'll plug in the top value and we'll plug in the bottom value and subtract those. I think most everybody knows that the inverse sine of the square root of 2 over 2 is pi over 4. Sometimes people get a little confused on some of the other ones, and a lot of times when I'm evaluating inverse trig functions, I draw a quick triangle. This is one of our special triangles. It's a 30-degree or pi over 6 triangle for the inverse sine of 1/2. So what I'm going to get is 2 times the quantity pi over 4 minus pi over 6, and a common denominator there quickly. Our common denominator is going to be 12, and that's going to give me a numerator of 3 pi minus 2 pi. And 3 pi minus 2 pi is 1 pi, obviously. When I don't forget to multiply by that constant of 2, so I get a final answer of pi over 6. Pretty tricky problem, lots of steps, inverse trig functions.